just going to pick up where we left off in the last video. So in the last video, I finished off by talking about endothermic and exothermic reactions. Endothermic heat moves from the surroundings into the system, which causes the temperature to drop, and the container for the reaction to feel warm. On the contrary, in an exothermic reaction, heat is released, which causes temperature to go up, and the reaction feels hot. So, how do we measure heat flow? So we've talked about situations in which heat will be, we will have heat flow, we'll have thermal energy either leaving the chemical reaction or entering the chemical reaction, and we want a way to measure that change in energy. So we're starting to talk about using math to quantify the energies. And we have a formula for that. So this is a formula that allows us to quantify thermal energy or changes in thermal energy. So quantify comes from the word quantity, which has to do with amount. So when we talk about quantifying thermal energy, we're talking about measuring how much of it a substance either absorbs or releases. So we measure thermal energy or changes in thermal energy in the unit of calories. So calorie is a measurement of energy. And calorie is the unit we use to look at the transfer of heat. And so our formula is right here. And the way I would read this is Q equals MC delta T. This thing over here that looks like a triangle is actually the Greek letter delta. And in math and science, that Greek letter delta means change. And so delta T means change in temperature. And of course, whenever we talk about heat moving from one substance to another, we're going to have changes in temperature. And so the amount of energy that's either gained or lost depends on M, which is mass. We measure mass in grams, times C, and I'll come back to C in a moment, times the change in temperature. And change in temperature can be either in degrees Celsius or in Kelvin, but not Fahrenheit. So Q is thermal energy measured in calories. M is mass measured in grams. T is temperature measured in degrees Celsius or Kelvin. C is something called specific heat capacity. And we're going to look at specific heat capacity in more detail in an upcoming lesson. But I'll give you a brief overview of what it means right now. So specific heat capacity is a property of a substance. What that means is gold has its own specific heat capacity. Rubber has its own specific heat capacity. Wood has its own specific heat capacity. Every substance has a specific heat capacity. And what that is, it's a number, a measurement, that talks about how well that object or that substance can absorb energy. Some substances can absorb lots and lots of energy and not change their temperature very much, whereas other substances absorb a little bit of energy and their temperature soars. And it just has to do with how the molecules interact in that particular substance. And so when you talk about thermal energy, and the transfer of thermal energy and how much energy a substance gains or loses, it depends on the properties of that substance, which is C for specific heat capacity, the amount of the substance we have, M for mass, and the temperature change, which is delta T. What you do need to know right now is that the specific heat capacity for water is 1. So anytime we're talking about water, specific heat capacity is equal to 1. If we're talking about a substance other than water, then I will give you the specific heat capacity for that substance. Okay, so we've talked about temperature changes in chemical reactions. This formula would allow us to figure out how much energy, how much thermal energy was gained or lost in a chemical reaction, so long as we had watched the temperature go up and down. So the question is, can temperatures change without chemical reactions? And the answer is absolutely. If I let, again, a plate of ice sit on the counter and just melt, the temperature is changing. There's no chemical reaction there. I'm just changing what I would call phase. I'm changing the ice from solid to liquid. So you can have temperature changes all over without necessarily having chemical reactions. And what that's called is thermal equilibrium. So this is one of the last concepts you saw. It's the concept of thermal equilibrium. So thermal equilibrium says that when two objects are in contact, that means there's some part of their surfaces that are touching, they will eventually reach the same temperature. So once that happens, we say they are at thermal equilibrium. So again, I'll use the ice example. If I take a plate of ice and leave it out to sit, it will eventually melt until it reaches thermal equilibrium with the air. There will be a transfer of heat from the air to the ice until those molecules in the ice and in the air start moving with similar motions. Remember, all temperature is the motion of the particles. So from the top, heat is not a substance, it's a process of energy transfer. Anytime I have two objects in contact with each other that are different temperatures, heat will move from one to the other until they reach the same temperature. And you saw this in the demo in class when you put one hand in hot water, one hand in cold water, and then moved them both to be in room temperature water. The hand that had been in hot water had heat leaving it, and so it started to feel cold. But the hand that had been in cold water, once it was put in lukewarm water, had heat entering in order to reach thermal equilibrium, and so it started to feel hot. And what that brings up is that perceptions of temperature and heat are relative. What I experience as being hot or being cold depends on the temperature that I already am. So that is it for my first thermodynamics video. We can pick up in class. If you have any questions or things that you're unsure about, I would encourage you to go through your notes, write down questions, and then actually ask them in class so that you can get things cleared up.